Welcome to video G in our series for the AP Calc Summer Assignment. This is on the section on asymptotes, which is section G of the summer packet. So I want to remind you of some things. Remember, an asymptote is an imaginary line that is not really part of a graph, but it's a characteristic of a graph. And it's a line that the graph of a function approaches, but will never actually cross. And there's two types of asymptotes that you can see. There are vertical, and there are horizontal. There's also kind of a subset of asymptotes called holes, which another name for those is a removable discontinuity. Okay? One of the things we're going to study a lot this year is we're going to try to come up with a lot of different characteristics of functions, and one of those things is trying to come up with where the function is discontinuous. Where are there any asymptotes? Okay, and some of the rules related to that you've seen already in pre-calc. Let me just quickly review them and do a couple examples. So if you're asked to find vertical asymptotes, all you basically do is you set your denominator to 0 and solve. Okay, these are just the values of x that would make the denominator 0, hence make f of x undefined. Because remember, since vertical asymptotes are vertical lines, they're going to hit the x-axis, so we're looking at particular x values that don't work for a function. Now, horizontal asymptotes are a little bit different. Horizontal asymptotes, what you're going to be doing is you're going to be checking the highest power and seeing where in your function the highest power is. If the highest power is in your denominator, then the horizontal asymptote is the x-axis of the line y equals 0. If the highest power is in your numerator, there is no horizontal asymptote for that function. If there's a tie, and the highest power can be found in both the numerator polynomial and the denominator polynomial, then basically it's going to be the horizontal asymptote at the line y equals the leading coefficient of the top over the leading coefficient of the bottom. So the tiebreaker is basically going to be your coefficients. Okay? By the way, this all is related to asymptotes, asymptotes are all related to rational functions, right? We're going to be looking at functions of this form, f of x equals g of x over h of x, where g and h are polynomials. These are the so-called rational functions. That's where you're going to see your asymptotes, because since you're dealing with division and being a rational function, that's where we have that potential for an asymptote. So let's look at some examples. So the sorts of things that we're asked to find are vertical asymptotes, horizontal asymptotes, and holes for some given rational functions. So here's one. F of x equals 3x plus 3 over x squared minus 2x minus 3. Now, before I start playing around with this function, I want to do some factoring, because it's quite possible that this rational function can be reduced. And if it does, and it can be, then we have to start talking about the third thing that I left out in the last slide, a hole. So for the top, I took the liberty of taking out the GCF of 3, and I'm left with x plus 1. The bottom, I want two numbers that multiply to negative 3 and add to negative 2. Well, that's plus 1 and minus 3. Well, look what just happened. I can actually cancel out the x plus 1s and be left with 3 over x minus 3. That's important for when we get to holes in a second. So we'll start with our vertical asymptotes. We look at our denominator of the reduced fraction. X minus 3 cannot be 0. So x cannot be 3, which means I have a vertical asymptote at x equals 3. Okay, well, what about the x plus 1 that we canceled out right here? Do we use that as a vertical asymptote? No. This is where the hole is. Anytime you cancel out a factor in a rational expression or rational function, that's where you're going to have your hole. So there's a vertical asymptote at x equals 3. There is a hole at x equals negative 1. Now to get our horizontal asymptote, we look at the degrees of f of x. The numerator has degree 1. The denominator has degree 2. Highest degree is in the denominator. So as we said in the last slide, that means our horizontal asymptote is going to be at the x-axis, y equals 0. Okay? So you have actually a pretty good idea of how this graph is going to look without really doing much sketching. You know you're going to have a vertical asymptote at 3. You're going to have a horizontal asymptote at y equals 0. And there will be a hole at x equals -1. So the curve will get close to -1, then there'll be a little open circle right at x equals -1, and then it will continue where you left off. Let's try one more. Let's look at the function let's call it g of x equals 2x squared minus 4x over x squared plus 4. All right. So, we can see if we can reduce. But we can't, at least not the denominator, because x squared plus 4 is not factorable. So since it's not factorable, that means there's no real solutions to setting that equal to 0. So that means there are no vertical asymptotes for this function. This is going to work for any value of x. There's no holes, because again, I can't remove any factors, so I won't have to worry about holes. Let's think about horizontal asymptote. Okay, so we'll look at our degrees. The numerator is degree 2, but so is the denominator. So that means our tie goes to the coefficients, 2 over 1. So there's a horizontal asymptote at y equals 2. Okay, again, not asking you to do any really sketching of these graphs on the summer assignment. We will do some of that this year. Just want to come up with identifying where those asymptotes would be based on the equation. Thank you for watching.